Hello everyone, welcome back. Today we're going to look at our second module on coordination, this time with a cognitive neuroscience perspective. So what we're going to look at is what is it about our nervous system, our neurophysiological connections between the brain and muscles that contributes or causes coupling. Put that in another perspective. So in the last module, we saw lots of examples of spatial coupling, temporal coupling, and spatiotemporal coupling. And on this slide, switch to my laser pointer. On this slide here, we can see Kelso's experiment, his first experiment, where he showed temporal coupling for bimanual asymmetric movements. And then in Kelso's second experiment, this is where they showed spatial coupling in, again, bimanual asymmetric movements where the left arm was going over a block and the right arm didn't have a block, but in some participants, the arms coupled together. Let's see, other examples that we saw Walter and Swinnen's example of one arm doing a unidirectional movement, the other one doing a double reversal at the same time. That's hard to do. We saw Fran's experiment where you have to try to draw a circle with one hand and a line with the other. And we're going to see a good example of that one again today. So in these cases, we saw spatiotemporal coupling, sometimes spatial, sometimes temporal, sometimes both, spatiotemporal coupling. And we argued that this occurs because we are constraining our movements, we're reducing the degrees of freedom, or in other words, we are simplifying the challenge to the executive to control the many degrees of freedom of the motor system. What we're going to see today is that the way we're wired, the way our nervous system is connected, also contributes to coupling. It's not just a cognitive psychology phenomenon, but it's also built into our cognitive neuroscience. And hopefully that makes sense as we look through 3 examples. The first example we're going to look at are ipsilateral corticospinal axons. And hopefully corticospinal axons is familiar because these have come up a few times in the course. So early on we talked about the idea, a very simple, straightforward notion of our neuroanatomy, that if you need to move your, let's see, my right hand, I had to check which hand it was, that most of that motor command comes from the contralateral or opposite motor cortex or cerebral cortex. So most of this motor command is going to be sent out from my left hemisphere. It's going to go down the left side. It's then going to cross at the kind of level of the brainstem, crosses over to the other side of the brainstem, and this crossing we call a decussation. So it crosses, then it continues to descend on the same side as the hand until it gets down to the appropriate level of the spinal cord to send that motor command out to those muscles. So these are contralateral corticospinal axons. And the contralateral ones are the majority, or even the vast majority, of corticospinal axons. So much so that sometimes we just say corticospinal axons. We don't bother adding contralateral because we just kind of assume that's how they all work. The interesting thing, though, is most of our corticospinal axons are contralateral, but some, a minority, are ipsilateral. And that's shown here. So here we have our contralateral corticospinal axons, kind of the ones we think about, and they descend and then they cross to go to the opposite side of the body. So here, your right hemisphere would be sending a motor command to your left hand, for example, or to your left foot. This is most of our corticospinal axons, about 85 to 90% in most individuals. There are, however, ipsilateral corticospinal axons. And here, if we're sending a motor command out to our left hand, that originates from the right hemisphere, and most of those corticospinal axons take that command to the left hand, 90% we'll say, but 10 to 15% of the corticospinal axons remain ipsilateral and would end up sending that motor command to the right hand. So if I'm standing here and I want to send a motor command to my left hand, 90% about of that motor command is going to my left hand, but 10% via the ipsilateral corticospinal axons want to go to my right hand. Now, I've learned to live with this as we all have. We're not consciously aware of the wiring of our nervous system, but when I'm producing this movement, my nervous system is actually preventing a motor command, 10% of that motor command, to go to my right hand. Now, if it did, what would happen is you would see probably a little movement in the unintended hand. And that's from the 10 to 15% of ipsilateral corticospinal axons remaining ipsilateral, and if you will, going to the wrong hand. And we call these mirror movements. Now, mirror movements can be seen in two cases, but in yourselves, likely all young adults, this is something that your nervous system has learned to compensate for, so it's not typical to see mirror movements in me or in a young adult. Where we can see them are in children. That'll be our second example. The first example we'll look at is a genetic condition. Let me see if I have any notes on this here. Yeah. So this is a specific genetic condition. There's two different names for it. Sometimes it's referred to as Bimanual synkinesis. Not sure if I'm pronouncing that right. Or more simply, the terminology I like to use is mirror hand syndrome. And people with this genetic disorder, what happens is instead of the typical 90% contralateral, 10% ipsilateral, they have far more ipsilateral than in most neurologically intact individuals. And someone with mirror hand syndrome might have 60% contralateral corticospinal axons and maybe 40% ipsilateral. So when they're a young adult, even as they've lived with this condition for a long time, when they want to send a motor command out to the left hand, a lot of that inadvertently goes to the right hand. For neurologically intact individuals, it's not hard to learn to suppress those 10% of fibers. But now imagine 40%. You can still learn to suppress them, but it's much harder. Liz France, so the researcher we saw earlier with the circles and the lines, she investigated a family with this genetic condition, and it ran through generations of the family. The dad, he learned to play a 12-string guitar, so very difficult bimanual asymmetric movements. He could still do them. It would have taken more practice than someone without mirror hand syndrome, but it's still possible. A son in the family learned to drive a motorcycle. And you can imagine you have to do different things with your hands to control the gas and the brake, and you don't want to mix these up. You don't want to do both at the same time. So it was of vital importance that he learned to do this without spatial temporal coupling. Let's take a look at this video. Give it a watch, and what you're going to see is someone with mirror hand syndrome playing the piano. And at first they're going to play with just one hand, and they're not going to fight to suppress the mirror movements in the other. And you're going to see they're quite large because they have more ipsilateral corticospinal fibers than normal. Then they'll play with the other hand, and you'll see mirror movements in the opposite hand. But then they're going to show that yes, they can play the piano, they can suppress these mirror movements, but it would take way more effort than it would for a neurologically intact individual. The second way that we can see mirror movements outside of a genetic condition is in babies and children. Now, we're born with this distribution of ipsilateral and contralateral corticospinal axons, and as we grow and develop, we learn to suppress those mirror movements. But they're not completely suppressed in children. So here's an example. This is my son Elias when he was 10 months old. The challenge with the 10-month-old is we don't know exactly what he's trying to do. So he's got this rattle in one hand, and what I think he's trying to do is just shake the rattle. And what you're going to see is that there are mirror movements in the other hand, especially when this movement becomes very vigorous. Because you imagine the larger the motor command he sends to this hand, the larger the potential mirror movement in the other hand. So is he just trying to do this and this is a mirror movement? That's possible. It's also possible that he's just trying to shake both hands. and with an infant, we don't know which is the case. But let's take a look. So you can see, let's go back. You can see the one hand is the rattle, and as those movements get big, the other hand, what we might be seeing are mirror movements. Let's look at it again. So especially at the end there, it's possible those are mirror movements. Now you still see mirror movements in young children, although they're getting smaller and smaller as they learn to cope with these ipsilateral corticospinal fibers. So here's my son now 3. The benefit of being 3 is we can give him instructions and we know that he understands them, or we can talk to each other about what he's trying to do. So I've asked him to try to just shake this rattle in his right hand, and I asked him to make the movements even bigger, because the larger motor command to one hand, the more likely we're going to see mirror movements in the other hand. So let's take a look. Okay, do it again. Try shaking nice and big. So you can see there, right at the end, these really big movements.
All right, good job.
As the movements get big, the other hand seems to do the same thing. And those are probably mirror movements. And we can't say for sure without kind of recording motor activity, but probably what we're seeing there are mirror movements. So that is our first neurophysiological source of coupling. One reason we see spatial temporal coupling is because when we try to send a motor command just to one hand via the contralateral corticospinal axons, that motor command is also potentially sent to the hand on the same side via the ipsilateral corticospinal axons. So almost by default, the two hands want to do the same thing at the same time, i.e. spatiotemporal coupling, because the corticospinal axons work that way. The second source of coupling is the corpus callosum, the large band of fibers that connects the two hemispheres. The two hemispheres, the left and the right hemispheres, are connected via a few different structures, but the corpus callosum is by far the largest. Here's a couple images of the corpus callosum. If we spread the hemispheres apart, you can see the large connective tract between them. And the corpus callosum is a very large structure, so big that there are names for different parts of it, because the corpus callosum, more anterior versus posterior, connect different parts of the brain and have different roles. So it's a very big structure, the main connective structure between our two hemispheres. So let's try to understand the corpus callosum's role by looking at an individual who doesn't have a corpus callosum. So in this external video, we're going to look at Joe, an individual who had his corpus callosum cut on purpose. He had surgery to help his epileptic seizures. This is still a surgery that's done, although you have to have the right type of epilepsy for this surgery to help. The way it helps, or the individuals that it helps, is if you have epilepsy that first isn't controlled well by medication, because medication is the first type of thing to help. Of course, taking medication is easier than having brain surgery. So if medication doesn't help, and the type of epileptic seizures you have begin in one hemisphere and then spread to the other hemisphere via the corpus callosum. And once you're having a seizure in both hemispheres, you would become incapacitated, you'd probably fall down, and it would be, of course, very disruptive to your day. So if you have those type of seizures, what they can do is they can cut the corpus callosum, and now if you have a seizure in one hemisphere, it will stay isolated to that hemisphere. Without the corpus callosum, it won't spread to the other hemisphere. Now, I'm guessing you would probably still be aware that you'd be having a seizure, but without it spreading to both hemispheres, you would probably not be incapacitated. You might have to sit down, take a little break, but you're not going to, collapse, lose control of your entire body, because the intact hemisphere can somewhat compensate for the one having a seizure. So take a look at this video of Joe. We're going to see lots of really neat things in it. One specific example about spatial-temporal coupling, and then we'll come back and we'll talk about a few different things, because a lot of things we see here are going to relate to material that we've previously seen in the course. Before you watch the video, a reminder of some content we've previously seen. So remember that language processing, at least in most right-handed people, is mostly dominant in the left hemisphere. And face recognition, remember when we talked about prosopagnosia, that face recognition is dominant in the right hemisphere, and object recognition is dominant in the left hemisphere. And this is going to be important when we look at Joe and how he can process information independently in each hemisphere. Okay, let's talk about some of the things we saw there with Joe. So this is an example, bimanual symmetric and asymmetric movement. This is very similar to the drawing circles and lines, but now we're drawing three-sided rectangles. And if you ask someone to do this that has a corpus callosum, it's easy to do the bimanual symmetric movement, and it's hard to do the bimanual asymmetric movement. We see temporal and spatial coupling between the hands. Both hands want to do the same thing at the same time, and that makes it hard to do an asymmetric movement. And we've seen this several times. The neat thing is that when we ask Joe to do this, he has no corpus callosum, so his two hemispheres are largely independent. And because of that, he can do bimanual symmetric movements fairly easily, and he can also do bimanual asymmetric movements. He can draw these with far less spatial temporal coupling than in a neurologically intact individual. So in this case, it's actually better to have a severed corpus callosum. Okay, a couple examples of some of the independence of the hemispheres that we saw with Joe. So in one example, they flashed the word ship up to the right visual field. Now, that word is going to make it to Joe's left hemisphere, because remember, the visual cortices also have a contralateral mapping. Remember, the input contralateral, output contralateral. So he's going to perceive that word ship in his left hemisphere. Now that's good because his left hemisphere is dominant for language, so it can process the word ship. It knows what it's seen. And Joe can then speak ship. He knows that that's what he's seen. But what happens when we flash a word to his left visual field? Well, that's going to go to his right hemisphere, and that's kind of problematic because language is not dominant in this hemisphere. Now, in someone neurologically intact with a corpus callosum, that information would just cross the corpus callosum to get to the dominant language hemisphere. But Joe can't do that, so he can't say phone. What he can do, however, is he can use his left hand, which is connected to his right hemisphere, to draw a picture of a phone. And then when his eyes are looking at that, and both eyes see it, so the picture of the phone is going to go to both of his hemispheres, he can then realize that what the picture he's seeing is a phone, and then that kind of allows him to work backwards to realize, well, the word that his left hand knows must be phone. So it's very bizarre, because normally this communication happens, in a split second within our hemispheres, and now we're seeing it occurring, in the external world as he draws a picture. Very bizarre. Here's the last example we saw in the video where they tried a new experiment. So they showed Joe these pictures that were made up of objects. And this one, we have a face that's made up of flowers. So they flash it to his left hemisphere, so that information, to the left visual field, that will end up in his right hemisphere. And his right hemisphere knows how to do face recognition. So it looks at this and says, oh, I see a face. So we can then ask his left hand to point at what he saw, because the left hand is connected to the right hemisphere, and he points to the word face. I saw a face. Now the neat thing is they show that exact same image to the right visual field. That goes to his left hemisphere. Now the left hemisphere can't process face information, but it will recognize objects. So when it processes the same visual information, it says, hey, I see flowers. And he can report that by using his right hand, because that connects to his left hemisphere, and it points to the word flowers. So very interesting, the same visual information is uniquely processed by the two hemispheres. Now in a neurologically intact individual, even if that image went to just one hemisphere or the other, the corpus callosum would then share that visual information, and you or I, someone with an intact corpus callosum, would say, oh, I see a face, oh, and I see flowers. But Joe can only see one at a time. In the past, when I've showed this example, a few students have shared this video with me. And one thing about this is, unlike Joe, this isn't a documentary, so we don't know exactly how this person can write with both hands at the same time and in different languages. But my guess is that she might not have a corpus callosum. Now, she probably doesn't have the same situation as Joe, where she had surgery that cut her corpus callosum, because then she would know about it. But there are some people born without a corpus callosum, or born with a very small corpus callosum. So if you think of individual variability in any trait, like say height, some people are very tall, some people are very short, and there's a normal distribution connecting us, so most of us fall in the middle. And what this might be is a woman who was just naturally born with no or very small corpus callosum. That would reduce the spatial temporal coupling between the hands, which might be how she can write with two hands at the same time. So take a look at this video. The last neurophysiological source that we're going to look at is phantom limb. Individuals who had an injury, had the arm amputated, the arm is gone, they know their arm is gone, and yet they still have very vivid sensations of that limb. They can feel it. In some cases, they can also move it too. And this is called phantom limb. And we're not going to look at phantom limb in the same way we looked at ipsilateral corticospinal axons and the corpus callosum, but here we're going to use this unique condition as a way to test a hypothesis. And that is spatiotemporal coupling caused by motor output, so sending signals down, or open loop control? Or is spatiotemporal coupling caused by sensory feedback, or closed loop control? And individuals with phantom limb give us a unique way to test this hypothesis. But first, let's learn about phantom limb from this interesting video from Professor Ramachandran. And we're actually only going to look at the middle of this video from 10 minutes to 17:31, because in this video, Ramachandran talks about 3 conditions. They're all interesting, but only the middle applies today. If you want to watch the whole thing, though, the first part of the video is about Capgras syndrome, and the last part is about synesthesia, which are also fascinating topics. But make sure to watch the middle portion and then come back here. So phantom limb, very interesting, and solving this almost incurable pain with something as simple as a mirror box, obviously fascinating. But let's look at phantom limb as a way to test what causes spatial temporal coupling. So with phantom limb, the idea is that the motor output, or open loop control, is very similar in a neurologically intact individual and someone with phantom limb. Both of these people can send motor commands out to their two arms. The small difference, if you will, is that a person with a phantom limb, they can send that motor command out, although it will never reach its destination because the arm is gone. But the way that motor commands are produced and sent is really identical in individuals with phantom limb and someone who's neurologically intact. They can both send out motor commands. What's different in these two groups is sensory feedback. So someone with two arms, their brain receives sensory feedback from both arms. But someone with phantom limb, although they might have these vivid sensations of sensory feedback, there's only real sensory information from the intact arm. This other arm, the proprioceptors are missing, the Golgi tendon organs are missing. Those devices can no longer be sending sensory input to the brain because they are gone. That arm is gone. So the major difference between someone with two arms and someone with phantom limb is sensory input or closed loop control. This individual, they can invoke closed loop control if they're moving this arm. This person can't use closed loop control because they're not getting any real sensory information from their phantom. So how can we use this to test the source of spatial-temporal coupling? Well, the first hypothesis is we are going to test people with phantom limb, and we're going to see whether they have spatial-temporal coupling between their real arm and their phantom arm. Now, if people with a phantom limb have no spatial-temporal coupling, then coupling must be caused by the sensory input, because that's the difference between someone with and without a phantom limb. Alternatively, if we test people with phantom limbs and they show spatial-temporal coupling, then coupling must be caused by the motor output, because that's still intact and it could still be what's causing coupling, because that is identical in individuals with and without a phantom limb. So Professors Franz and Ramachandran ran this experiment, and what they did is they went back to the draw a circle, draw a line task, and they had people do this with a phantom limb. Now, they asked them to draw the circle with their phantom limb. We're not going to be able to record that, of course, because that arm doesn't exist. But they asked individuals who had a vivid phantom that they could move, and they said, okay, draw a circle with your phantom. So we'll have to trust that that's what they're doing. Then with their real arm, they asked them to draw lines. And the question is, do we see spatial-temporal coupling in their real arm? Instead of lines, are we going to start to see ovals because there's spatial-temporal coupling between their phantom and their real arm? Now here are the actual results. We can't record a phantom limb, so we don't see anything there. But what we saw in their real arm is that there is spatial-temporal coupling between their real arm and their phantom, which is kind of fascinating because you're spatial-temporally coupling with something that doesn't exist. So why does this happen? Well, this is explained by our second hypothesis. So recall that people with a phantom limb are still sending out motor commands even though the arm is not there. And it must be that just generating and sending out these motor commands, or the open loop control, is what causes spatial-temporal coupling, because this is intact in people with phantom limbs, and we still see spatial-temporal coupling with a phantom limb. So in other words, spatial-temporal coupling is not caused by sensory feedback, because we got rid of this in people with phantom limbs and coupling still persisted. So it must be the output of those motor commands or open loop control. So just to summarize phantom limb, because this is a kind of an unusual experiment. So spatial coupling is not caused by sensory input. It's not caused by closed loop control. Spatial-temporal coupling is caused by motor output. It's caused by open loop control. So just the act of generating those motor commands for each arm, sending them out, even though one motor command isn't going to get there because you have a phantom limb, is enough to cause spatial-temporal coupling. So those are our three neurophysiological sources of coupling. So take a look at the sample questions and good luck on the test.